Hello and welcome to another stat video designed to get you ready for the final exam. So let's see what we have here. Event A has a probability of 23%. Event B has a probability of 44%. If A and B are disjoint, mutually exclusive, then the probability that both events occurs is what? So this is really just knowing the definition of mutually exclusive. And if we think kind of Venn diagram style, mutually exclusive is when the two circles do not overlap at all. So the probability that both events occur is 0%. Right? That's kind of the definition of mutually exclusive. I'll just add that there. It's pretty much the definition of mutually exclusive. If one occurs, you know the other one cannot occur. So the odds of them both happening are 0%. All right. Number 2, in a particular game, a fair die is tossed. If the number of spots showing is either 1, 2, or 3, you have to pay $1. If it is 4 or 5, you win $1. If the number of spots showing is 6, you win $4. Let X be the amount you win. What is the expected value of playing the game? All right. So 1, 2, and 3 represents half the die. So there's a 50% chance, or half, 1/2, that you are going to lose $1. All right. 4 or 5 represents two sides of the die. So you could think of that as 2/6, or 2/6 reduces to 1/3. So there's basically a 33% chance that you're going to win $1. And then if the number is a 6, you get to win $4. So that means that there's a 1 in 6 chance of getting $4. All right. Now, could you have done this on the calculator? Yeah, you could have. All right. You could have gone to stat edit and said, all right, my payouts are -1, 1, and 4. This one has a 3 in 6 chance of happening. This one has a 2 in 6 chance of happening. This one has a 1 in 6 chance of happening. All right. And then you could go to stat calc, one variable stats. List 1 is your payouts. List 2 is your frequencies. And that'll tell you that the average of those is 0.5. But all that is really doing is this right here. All right. And if I were to type this in manually, 0.5 times -1 plus 1/3 times 1 plus 4 times 1/6. All right, I'm going to get the same answer regardless. So whichever way you do it doesn't really matter. You're going to get the same answer regardless. Okay? So just this idea of an expected value is really sort of a weighted average. And then you can get those values from there. So the weights of pineapples of a certain variety are approximately normally distributed with a mean of 1.2 and a standard deviation of 0.23. What is the probability that the total weight of 3 randomly selected pineapples is more than 3.4 pounds? All right, so again, this gets into combining random variables. So if each pineapple is a random variable that follows this distribution, this is basically asking, all right, what happens when you combine those 3 random variables? All right. Well, we know our new mean is just going to be 1.2 plus 1.2 plus 1.2, which is 3.6. And our new standard deviation, we don't get to add the standard deviations together. We have to add the variances and then turn it back into a standard deviation. So adding the variances would be 0.23 squared plus 0.23 squared plus 0.23 squared. That's us adding the variances. And then we're going to take a square root to turn that back into a standard deviation. All right, so 0.23 squared is that. And then I'm just going to multiply it by 3. And then I'm going to take the square root of that. And we end up with a new standard deviation of 0.3984. All right. Once we have these two values, now we can use our NCDF. So we can say, all right, what are the odds of getting something 3.4 or higher when the mean is 3.6 and the standard deviation is 0.3984? All right. So we would go to our second vars, normal CDF, 3.4 to 9999 with a mean of 3.6 and a standard deviation of 0.3984. And we'd end up with 0.6922. All right. So that's going to equal 0.6922, which you can leave as is, or you can write it as 69.22%. Either way is fine. Okay. But again, this idea of combining random variables, getting a new mean, getting a new standard deviation, and then using NCDF to calculate a probability from that. All right, number 4, a worn-out lid-making machine does not properly size the lips in 5% of cases. That's a shame. If you randomly select 20 lids from those produced by this machine, what is the approximate probability that between 3 and 7 inclusive, lids have been improperly sized? All right, so we're selecting 20. All right, I'm going to write out something quick to make this visual a little easier to understand what we're doing. 11. And then we can go ... 20. All right. So what we're looking for is we're looking for these probabilities right here. All right. What's the probability that there were 3 misfitting lids, plus the probability of 4, plus the probability of 5, plus the probability of 6, plus the probability of 7? All right. Now the problem tells us we're going to use a binomial distribution here. So we know that in our toolkit we have binomial CDF. So if we do a binomial CDF where there are 20 trials and the chances of a lid not fitting is 5%, 7, this will give us 7 down to 0. All right. But we don't want 7 down to 0. We only want 7 down to 3. So what we're going to do is we're going to subtract away 2, 1, and 0, and that will leave the correct answer. So we're going to subtract away those 3 to get what we want. So binomial CDF, still 20 trials, still 0.05, but this time we're going to put a 2 in there. And by subtracting this away, it leaves 3, 4, 5, 6, and 7, which is what we're looking for in this question. So we can do that on the calculator here. Distribution, binomial CDF. We had 20 trials, 5%, and we want to know 7. All right. That's going to give us the first part. I think I typed something in wrong. Let me see here. Binomial CDF 20.05. Nope, I've got everything in there, right? I got a little worried when I saw all those 9s, but that makes sense because if there's only a 5% chance of one not fitting, the odds that 7 or fewer are not going to fit is going to be really, really high. So we're going to keep those decimals, 999, 1, 2, 3, 4, 5, 7, 1, 4, 3, 1. And then we're going to subtract the odds of 2 or fewer. So binomial CDF, the only thing I have to change here is to 2. That's going to give us 0.9245, 163, 263. All right. And then I can subtract those two values. So let me just type that in quick. 99999,71431 minus an answer. All right. And you're going to get something like 7.5% about. So we'll round this now to 0.0755 or 7.55%. Okay. So again, knowing how to use binomial CDF, taking the information from the problem, all right, the 20 is your sample size, the 5% is your probability, and then this 3 through 7 is what you're using to actually find. That's the X value that you're putting into the calculator. All right. And this one was just a little different because it required you to kind of say, all right, this is going to give me 7 to 0. If I only want 3 to 7, I have to subtract away 2, 1, and 0. All right. Let's take a look at the back. A poll shows that 20% of adults in a large town are registered Free Soil Party members. A newspaper reporter wants to interview a local Free Soil Party regarding a recent improvement plan for Lindenwold. On average, how many people will the reporter have to stop before she finds her first Free Soil Party member? All right, so this is basically the expected value of a geometric distribution because we're counting how many tries until our first success. All right, and what we learned is that's found just by doing 1 over p. So in this case, it would just be 1 over 0.2, which would just equal 5. All right, so pretty easy as long as you knew what it was asking for and then the appropriate formula that you have to use with that. Number 6, according to a recent poll, 6% of Americans watch less than 20 minutes of television in a week. Let's assume that this is the parameter value for the population. If you take a simple random sample of 25 Americans and let p hat equal the proportion in the sample who watched less than 20 minutes of television, what is the mean and standard deviation of the sampling distribution of p hat? Okay, so the mean of p hat is always equal to the population parameter, which the problem tells us is 6%. So we know that the mean of our sampling distribution is just going to be 6%. The standard deviation of our sampling distribution is where we have to use our formula PQ over N. All right. So our P is 0.06, which means our Q is 0.94 because those always have to add up to 1. And then our sample size is 25 here. All right. So from that, we just put it in the calculator, 0.06 times 0.94, divide that by 25, take the square root, and we get 0.0475. Yep, 0.0475. All right, so the mean of your sampling distribution is 6% because that's the population parameter. And then the standard deviation of your sampling distribution, we have to use this formula for, and then we get 0.0475. Okay. Number 7, a newspaper conducted a statewide survey concerning the 2015 race for agricultural comptroller. The newspaper took a random sample of 1,200 registered voters and found that 785 would vote for the local candidate. Let P represent the proportion of registered voters in the state that would vote for the local candidate. Find the sample size needed to estimate P with a margin of error of 0.01 and 95% confidence. Use 0.5 as an approximation of P. All right. So 0.5 is generally what we use as the worst case scenario. So this is going to give us the largest possible answer. And if the problem tells you to use something different, you should use it. Otherwise, you kind of generally go with the worst case scenario. So formula that we need here is margin of error equals Z star times PQ over N. All right, the margin of error that we're testing for is 0.01. All right, Z star we're going to get using our inverse norm. All right, this is our critical value. All right, now because it's a 95% confidence, there's 5% left over, but we're going to do an inverse norm of 2.5% because that 5% is split between the left and the right. And then again, it told us we were using 0.5 and 0.5 for P and Q, and N is what we're actually trying to solve for in this case. All right, so inverse norm is in our distribution menu. All right, if I do 0.025, it is going to give me a negative 1.96, but we ignore the negative and just use positive 1.96. So 0.01 equals 1.96 times the square root of 0.5 times 0.5 over the square root of n. I'm just kind of rewriting this as two separate square roots. All right. At this point, it's really just sort of algebra. All right, I can multiply the square root of n by both sides and get 0.01 square root of n equals 1.96 times, and again, if you square 0.5 and then take the square root, you're just going to be back to 0.5. All right, and then this you really could just do on your calculator. So I could say 1.96 times 0.5. Then I have to divide both sides by 0.01. Then I have to square both sides to get rid of the square root. And I end up with an n of 96.04. All right, but that would be the sample size that I need there. All right, so 1, knowing this is the formula. 2, knowing how to find your Z star. And then 3, kind of doing the algebra correctly to arrive at the right answer. All right, number 8. If we reject the null hypothesis when in fact it is true, we have committed what type of error? All right, so we've committed a type 1 error. And again, this is when we reject the null and we're wrong. A type 2 error, so this is the one that, for this question, it's a type 1 error, but just because this is a study resource, a type 2 error is when we fail to reject the null and we're wrong. Okay, so again, just knowing the difference between a type 1 and type 2 error is something that is going to pop up on this test. All right, so hopefully this was useful. Obviously, if you have any questions, let me know. But again, all sorts of topics, all sorts of material that could show up on your final exam. So you want to be ready for that. All right, have a great day, and I will see you when I see you.